Okay, now we know how to use the information of derivatives to determine the interval of increase and decrease. In this video, I want to talk about how to use this result to find the local maximum and the local minimum of a function. So first, we're gonna look at something called the first derivative test. Now here is the first derivative test. Let C be a critical point of a function fx that is continuous on an open interval. On an open interval I containing this critical point. If the function is differentiable on this interval, except possibly at C. So that means at C, the derivative could not exist, because we know when the derivative does not exist at C, C could also be a critical point. Then the following gonna be true. One is if the derivative changes from negative to positive at C, then the function gonna have a local minimum at the point C f of C. If the derivative changes from positive to negative at C, then the function gonna have a local maximum at the point C f of C. If the derivative does not change sign at C, then the function does not have a local maximum or minimum at the point. Now, so how to understand this test? So let's say if the derivatives changes from negative to positive, that means the function changes from this is the derivative. That means the function gonna change from decreasing to increasing. So therefore, at C, at this point, the function gonna have a minimum value, and the minimum value is the function value f of C. And if the derivative changes from positive to negative, that means the function changes from increasing to decreasing. So at this point, the function has a local maximum. Now, when the derivative doesn't change the sign, say the derivatives are both negative, so the function gonna be decreasing and then decreasing. So therefore at C we don't have a local maximum or minimum. And similarly, if the derivative are both positive, the function gonna be increasing before C and increasing after C. Okay. So this is what does the first derivative test say. Okay. So to find the local maximum and minimum with the first derivative test, we can follow this procedure. First, we take the derivative, and then we find the critical points, and then we divide the number 9, or we divide the domain of the function by using those critical points. And then we determine the sign of the derivatives on each interval using the test point. And so we can know which interval the function is increasing and on which interval the function is decreasing. And then at the end, we use the first derivative test to determine if any of the critical points are local maximum or minimum. Okay, because if the derivative doesn't change sign, and at that critical point, we do not have a local maximum minimum. Only when the derivative changes the sign, that critical point, we have either maximum or minimum. Okay, so now let me use this example. Okay, let me find the local maximum and minimum for this function. Fx equals 3x to the third plus 4.5x squared plus 7. Okay, so first we're gonna take the derivative of this function. So that is 9x squared plus 9x. In the second step, we found the critical point. So I set up this equation, which is equivalent to 9x squared plus 9x equals 0. Again, since this derivative function exists everywhere, so we only have one place to find a critical point. And to solve this equation, we can factor out 9x. So we have a 9x equals 0 and x plus 1 equals 0. So there are two critical points. In step 3, we divide the number 9 using these two critical points. On each critical point, on each interval, we choose a test point. So here, let's see, I use -2, and here I use -0.5. Here I use +1. And then I plug each test point into the derivative function. And to see whether it's positive or negative. Okay. And again, here is the technique. Since I already factored this derivative function into this form, so I can use this function. Okay. So when x equals -2, we have 9 times -2 times -2 plus 1. This is negative times -1, so that's positive. Okay, now when x equals -0.5, it's 9 times -0.5 times -0.5 plus 1. This is -0.5 times +0.5, that's negative. And when x equals 1, this is 9 times 1 times 1 plus 1, that's positive. Okay. So therefore the function is increasing on the interval from -infinity to -1 and decreasing from -1 to 0 and increasing from 0 to infinity. Okay, after we found this information, then according to the first derivative test, or from the sketch of the graph, we can see that the function gonna have a local maximum at -1, and the function gonna have a local minimum at 0. So fx has a local maximum at x equals -1, and a local minimum at x equals 0. If we want to find what is the local maximum and local minimum, this time we are going to use the original function. Okay, we're gonna use the original function. So we plug -1 into fx, so we can find the maximum value, and we plug 0 into the function, we can find the minimum value. So the maximum value is 3 times -1 to the third plus 4.5 times -1 square. So that's that is -3 plus 4.5 plus 7. So it's 1.5 plus 7. So it's 8.5. So the maximum is 8.5, and the minimum, the local minimum is so when x is 0, 0, 0 plus 7, so it's 7. Okay. Okay. Now let's use let's verify our result. Okay. So fx equals 3x to the third plus 4.5 x squared plus 7. Now we can see so we have a local maximum, right, at -1 and a local minimum at 0. Now remember, these are not the absolute maximum and the absolute minimum. They are only the local maximum and minimum, because this function is defined is not defined on a closed interval. So we cannot guarantee the existence of absolute maximum and minimum. We can only find the local maximum and minimum for this problem.